Hello, everyone. Welcome to today's webinar. Steve, people are still arriving, so give us 2 minutes before we start. Hello, everyone. Thanks for joining the webinar today. My name is Nick Payton, and in a second, I'll introduce Scott Clark, SigOpt CEO. We'll spend today's webinar discussing a few key lessons for modeling at scale and systematic trading. We'll run through any questions at the end of the presentation, so be sure to use the question asking functionality in GoToWebinar to ask as we proceed through the presentation. I'll collect them and then make sure that we get to each of them by the end of the discussion. So for today, Scott will be leading the discussion. And before we jump into the lessons for modeling at scale, Scott, will you provide background on SigOpt?
Definitely. Thanks, Nick. I'm really excited to chat with you all today. So I'll start with a broad overview of how I got to where I am today and built SigOpt, and then dive into how we help various systematic traders and different lessons we've learned from doing that over the last few years. I got started in the field of optimization during my PhD work at Cornell, mostly applying it to different problems within the Department of Energy and various mathematical simulations, but eventually found my way into industry at Yelp, where I realized that there was lots of tunable systems throughout industry. This is obviously extremely pervasive in the asset management space, but within the consumer space, it's a lot of advertising, recommendation systems, etc. To help solve this problem, I took some of the research I had done at Cornell and open sourced a package called Mo, or the Metric Optimization Engine. We quickly learned, though, that an open source solution to this problem usually fails when it comes to really large scale enterprise needs and the ability to really trust this when you put it into production. And so about 5 years ago, I grabbed my smartest friend, Patrick Hayes, and we formed a company to help solve this problem once and for all, really democratizing the ability to use the best of the Bayesian and global optimization literature behind a simple API that can scale with your needs and now services customers around the world. A few rounds of funding by Andreessen Horowitz later, and here we are today working with firms in the asset management space that I'll get to in a second, but also the US intelligence community, the tech industry, global technology consulting firms, and more. Basically, everybody has an optimization problem, and we're a way to help address that very seamlessly and scalably. But the focus of this talk is primarily around asset management and how can optimization help bolster a broader strategy for doing this well. And it goes without saying, and any of you that are on this webinar now already know that quants and algorithmic methods are eating Wall Street. It's not just software eating the world, it's quants and models really taking over what was historically an extremely qualitative business. And SigOpt has seen the rise of that as well over the last several years, helping many different firms around the world that have a combined total assets under management of several $100 billion. We see day in and day out the needs and the solutions that some of these firms use in order to continue to grow their assets as well as get an edge over the competition. So we've designed SigOpt explicitly to be very IP safe and data safe and secrecy safe to begin with, which means that I'm not going to be able to dive into a lot of all of the different firms that we work with. but one recently kind of stood up and did quite an extensive use case and deep dive into why they chose SigOpt, how they chose SigOpt, and as part of this larger strategic relationship, we formed a partnership with 2 Sigma. So a lot of this talk will be centered around how we work with them and some of the insights that they were able to draw and then publicly discuss. But it also draws upon some of those other firms that can't be named yet, but represent, again, much larger assets under management in aggregate. So over the course of this webinar, I'm going to go over 5 main lessons that we've learned that we've seen work very efficiently when it comes to really, again, being modeling driven and getting that edge when it comes to this market. The first of which is investing in a reproducible process. This allows you to iterate faster, try things faster, etc. Some of this comes with picking the right tools and deciding what's worth building, what's worth buying, what's worth kind of pulling off the shelf, whether it be open source or different cloud providers, and that's that balance and flexibility with the standardization. Then it's about picking the right tool for the job. There's certain things that humans are incredibly good at, understanding contextual awareness, having domain expertise, etc. And there's certain things that humans are incredibly bad at, like doing high dimensional optimization in their head. And it's really about maximizing resource utilization and, at the end of the day, prioritizing performance. You care about making as much money as possible, as quickly as possible, and keeping whatever edge you have as long as possible. And there's different things that you can do to do that or do it iteratively faster. So I'll dive into each one of these in detail, but this will be the scope of the talk. So first up, investing in a reproducible process. What we've found at the very broadest level, there's 5 pillars that go into building an algorithmic trading firm, or to really getting the best possible edge. You need data, you need modeling, you need a simulator or backtest to kind of validate those models. You need a way to optimize those models with respect to that simulation or backtest in order to get to the best possible results. And then finally, you need to be able to put that into production so it can actually execute on the global markets. And each one of these steps requires different trade-offs, different pitfalls you need to avoid, etc. So the first one goes without saying. Data is extremely prevalent. Being able to find non-correlated data that ideally gives you some sort of insight or edge in the market is incredibly important. And this goes beyond kind of the statistical analysis of just looking at historical stock prices, of course. This is looking at maybe company data, their SEC filings, the news, their tweets. There's been an explosion of this over the last decade or two, taking it all the way from just what people are saying, all the way to maybe what satellites are showing about the parking lots. If you can correlate the number of cars in a parking lot to their earnings, that could give you a little bit of extra information to make some sort of trade or edge. And this is only continuing to explode with the growth of social data, location data, etc. So I'm not going to get into the intricacies of this because there's many different feeds, many different companies that specialize in this. And oftentimes it's just getting the data is more of a commodity type problem. You just want to get as much of it as you possibly can so you can start to feed it into the models. And this is where domain expertise and contextual awareness really start to play a role. You can purchase data off the shelf, but then what you do with it affects what actually happens. This is where you can come up with your specific insights or whatever it may be and apply that to actually producing alpha. Now, obviously, there's been a large investment over the last few years from many top firms into machine learning and artificial intelligence here. It's become very common for people to hire heads of research or heads of machine learning from Facebook or Apple or Google or whatever it may be, and bring them in to start specific labs within firms. We've seen this across the board, and it seems like every few weeks there's a Wall Street Journal article saying AQR just hired somebody, 2 Sigma just hired somebody, whatever it may be. And a lot of this, again, is about picking the right tool for the job and then pointing it in that direction that you want it to go, and understanding what tool to choose And what you're actually gunning for, again, requires a lot of expertise and is not a one-size-fits-all problem. But once you've started to do this modeling, the next step is to say, how do I make sure I'm doing the right thing? How do I make sure that I'm actually shooting towards success and not towards some academic metric that might help me publish a paper, but ultimately will perform terribly out of sample? And this is really where simulations and backtests come in. And what we've found is that this is a core piece of IP that is usually unique per asset management firm. A good backtest can give you the confidence to say, I'm actually making progress as I ingest more data, do more feature engineering and modeling, and continue to kind of push the state of the art. But there's a lot of different pitfalls you need to worry about here. This isn't just taking the old stock ticker data and then trying to do a best regression fit or something like that, which time and time again they've shown in the academic literature will lead to terrible out of sample performance. So you need to make sure you avoid overfitting. You need to make sure that you're not looking ahead and cheating to see what, predicting the past based on the future. You need to make sure that you're actually taking into account some of these kind of more inherent biases to modeling itself, only looking at winners or testing on things that have survived long enough to be tested on, looking at a ton of models and then claiming that if one works, then it must have some sort of significance, when in reality, if you try 20 random strategies and one of them does well, but you only have 95% confidence that it does well, that's probably a random result. And then again, one thing that can be incredibly important, and I hinted at this a second ago, is biases in the metrics themselves. Very often in the academic literature, things are tested for accuracy, log loss, some of these kind of classic academic metrics that have incredibly great properties for proving theorems, but often are not correlated to actual performance when it comes to business impact. You could have a method that has the lowest RSME error when it comes to fitting a specific equity value. But at the end of the day, if it doesn't actually trade well out of performance, then even if you could have published a paper by beating the state of the art and getting it slightly more accurate, it ends up losing money. So it's important to think about things that you actually care about, like Sharpe ratio, or how much money was actually traded, or how much risk you were able to afford within your regulatory constraints. And this is really about, again, defining a simulation that you trust and then defining a measuring stick that actually correlates with what you care about as a firm. And once you have this, it's incredibly powerful. It makes everything else easier. It gives you a way to say whether or not a data set actually provided value, whether or not a model provided value, whether or not an individual quant was able to push the state of the art, et cetera. And ultimately, it turns the problem into an optimization problem. Now you have data, you have models, and you have a way to measure the efficacy of that data and modeling. And then you want to be able to get the most out of it. And this is about getting an orthogonal edge over whatever you've done so far. So you've, again, applied your domain expertise and contextual awareness to selecting the model and the data set, what metrics you're driving for, how to measure those metrics, et cetera. And now, ultimately, you want to take that system and configure it to maximize that value. And this is exactly where SigOpt comes in and how we help firms like 2 Sigma and others get the most out of these models. So what happens is they define the configuration space of these feature embeddings, these feature transformations, these feature engineered stores, whatever it may be. They define the configurations of their machine learning or deep learning or trading strategies. And then we suggest configurations for them to evaluate and backtest on that proprietary simulation or backtesting system. They report back one or more objective metrics with or without noise. And we learn from that. We decide, based off of what we've observed of configurations we've suggested, what's the most intelligent thing to suggest next. And fundamentally, this is hitting our optimization engine, this ensemble of Bayesian and global optimization techniques that are trading off exploration versus exploitation, learning more about the underlying space, and then exploiting that knowledge to drive to better local and eventually global optima. And what you get out of this is an extremely efficient way to tune the configuration parameters of these systems. Much faster than traditional methods from the academic literature like grid search or random search, but also significantly more efficient than things like more advanced variants of random search like hyperband or evolutionary algorithms or simulated annealing or particle-based methods. And the core concept there is, instead of optimizing the model itself directly, we're building up different probabilistic models for how the different configurations interact and how they affect the objectives you're driving for, and do optimization there, allowing ourselves to do quite a bit of work in flight and behind the scenes while you're evaluating the system, so that whenever you have a free resource, you're getting the most intelligent thing to try next. And we go into quite a bit more detail in our ICML, NeurIPS, and partner blog posts, papers, and various literature that is available on our research website. But at the high level, the goal is you have a model, you have a way to measure it, and you want to make it better. And we bolt on top with our simple REST API to do that without ever touching the model or the data. Finally, once you have a model that you like, once you have a model that you trust that does well on the backtest, etc., it comes down to execution. So this is the final pillar that's required to make a great asset management firm. You can do everything ahead of time and not do execution, and you've effectively just done research. And you can maybe paper trade and say that it works pretty well, but where the rubber really meets the road is how you're going to perform in the adversarial environment against everybody else. And this is where execution comes in. And again, this is something where potentially it can be commoditized if you're doing kind of lower frequency trading and you can work with a large investment bank to actually execute your trades. For some firms, this might mean higher frequency trading where they're using the state of the art of fiber networks or literally shooting lasers from building to building to get a microsecond edge. But at the end of the day, this is about, once you've come up with an idea of what you want to do, and you use that to build a model that you trust and have optimized to actually execute trades, how do you do that efficiently in the real market? And so this is similar to data in the sense that a lot of firms are using similar techniques, similar vendors, and it's largely commoditized. And where domain expertise can really play a role is in building the models and building that simulation or backtest. And then where you can get this orthogonal edge is when it comes to optimization. And that's really where we sit. So with those 5 pillars, if you do them right, if you invest enough PhD decades and engineering decades, you can have a great algorithmic trading firm. But then when it comes down to having those 5 pillars in place, it's more about how do you actually make sure that you're getting the most out of it? How do you continue to incrementally advance and really balance the flexibility that you need with the standardization that is required to do this at scale? And we see a lot of different stacks when we work with these global firms, both in the asset management space, but also in the larger technology space here in Silicon Valley. But you can loosely break it down into buckets around data, ingesting data, building features, etc. Experimentation, this is the actual modeling, the optimization, and the simulation I spoke about before, and the execution, the actual serving and monitoring of these strategies. And of course, underlining everything is this hardware component, which many firms have on-prem resources and potentially burst to the cloud, potentially doing arbitrage across the various clouds for various specific hardware needs or price-saving techniques. But when it comes down to deciding which of these you should build, which of these you should standardize, which of these you should leave to the individual quant or portfolio manager to decide what to do, we largely see 3 main questions being asked. On the solution front, is it standardized or does it need to be proprietary per firm? On the innovation side, is there incremental value from making it better, or can I bolt it onto a system that already exists? Or is it existential, in the sense that if you cannot execute, then you cannot trade, and then you're not an asset management firm? And what is the status of it? Is it something that's still evolving and getting better over time, or fully established and therefore can be commoditized? And when we look at these various components of the system, what we find is things like data, they're largely proprietary. You need to go to specific firms to buy the streams. The innovation is incremental. That new data stream might give you a slight edge until it becomes table stakes and everybody has it. The status is relatively well established. There's firms like Bloomberg that have been selling data feeds for decades. And the implication here is a little bit mixed. Sometimes it might be worth getting a specific edge by trying to go out and do it yourself. And other times you might be able to buy something off the shelf, or at least get 60% of the way there by going off the shelf. Similarly with modeling, there's a lot of different notebooks, libraries, and frameworks out there. They tend to change pretty frequently year over year. 10 years ago, everybody might have been writing their own based off of algorithm textbooks and papers. And then things like scikit-learn and NumPy, et cetera, started to standardize various aspects of the pipeline. And recently, a lot of that's been changed with things like PyTorch and TensorFlow. And I'm sure 5-10 years from now, there'll be a wide variety of frameworks around deep reinforcement learning and various other things that will continue to kind of push the state of the art. And the goal here is to make it easy for your experts to use the right tool for the job. They need to be doing modeling for you to be an algorithmic trading firm to begin with, but it's a constantly evolving field. So you want to maintain some level of flexibility here. For optimization, which is where we sit, a lot of the actual interface is standardized in the sense that every single model has these tunable parameters, and every single model has some way to measure success. And so it's very easy to bolt a solution on here and standardize without constraining on the modeling side, because a random forest with the number of trees that you need to set mathematically looks very similar to the number of hidden layers in a neural network. And the goal is to tune these in this black box way to drive towards whatever performance you define. The innovations here can be incremental in the sense that they bolt on top and can provide extra value on top of whatever you've already brought to bear to the system, and can capture a lot of upside that would otherwise be left on the table. They are constantly evolving though, so it's important to make sure that you don't invest in a single solution once and leave it. What might have been state of the art 10 years ago is definitely not the state of the art today, and making sure you invest in a solution that's constantly evolving and constantly pushing the state of the art is key to make sure that you stay on top of that edge. Simulations, again, as I mentioned before, are largely proprietary. A lot of IP goes into this. The innovation is existential. You don't want to trade live to test if your models are working or not. And there's relatively well-established ways to do this, both in the academic literature and just best practices. So again, this is something that you want to bring in-house and create something custom so that you can say, given my type of trading, given the asset classes I care about, given the frequency at which I trade, how do I really make sure that I can measure success? Finally, on the serving and monitoring side, as I said before, there's some standard solutions depending on how you're actually trading. You need to be able to build these, and it's existential to even have an asset management firm. And there are well-established ways to do this, whether that's specific investment banks that will execute trades for you, or specific ways to do various tradings on the exchanges themselves. And finally, hardware has largely become standardized, although we do see quite a bit of firms taking a very hybrid approach, going on-prem for their standard workflows where they know that they're going to be at capacity and they need very customized solutions, and then bursting to one or more clouds for various R&D efforts. And largely this space has been filled out in some of these areas, whether it's data companies that have been again around for decades, hardware environments like the clouds, various open source technologies for the modeling and the notebook environments, and SigOpt sits right in the middle, being that experimentation layer that again allows you to standardize without the constraints of a specific modeling type or a specific hardware simulation environment. You want to be able to say, everybody experiments, and we want a reproducible, trackable, shareable way to really introspect that while getting as many insights as possible, but without constraining what type of modeling they're doing or what metrics they're shooting for. And that's exactly what we designed SigOpt to do. And then when it comes down to after you've built the system, after you've started to cobble it together, after you've started to think about which pieces you're going to pull off the shelf, which pieces you're going to evaluate vendors for, etc., it comes down to how do you divide the labor between humans and machines? And one problem that humans are very bad at, like I hinted at before, is high dimensional optimization. An expert could know everything about the contextual awareness of where the model might trade, what data comes into it, what biases it might have, but tuning all of the different configuration parameters that go into it is a very arduous task. Imagine every single time you wanted to go somewhere, you had to jump into a plane like this and reconfigure all of these different knobs and levers. You could know everything in the world about what specific place you're flying to or what a specific mission you're going to, but at the end of the day, tuning all of these things via trial and error is a huge waste of that domain expertise. And whether you're tuning today or not, you're explicitly or implicitly already doing this. So whether you're doing it via brute force or cobbling together different brittle open source techniques or whatever it may be, you need to solve this problem in order to get the most out of your models, or you're leaving a ton of value on the table. And fundamentally, this is called hyperparameter optimization, although there's many different ways that people talk about it, whether it's model tuning, training and tuning, architecture search, hyperparameter search, etc. And as I mentioned before, there's many different ways that people have attacked this historically, from more simplistic brute force methods like grid search, to methods like randomized search, which have become popular in the academic literature lately, to evolutionary algorithms, Bayesian optimization, to old school methods like simulated annealing and particle swarm. And the idea here is not to take an optimization problem and turn it into an optimizing the optimizer problem. Different techniques work well for different states. Different techniques work well for different problem types, different dimensionality, different levels of parallelism, etc. And what SigOpt is designed to do is take all of this off your plate so that you can focus on your model and not focus on optimizing some optimizer or having to select an optimizer. And I'll dive into a little bit of detail for each of these kind of standard approaches and talk about the pros and cons. Depending on what you're doing, it might make sense actually to use one of these more simplistic methods. Something like a manual search has a lot of pros in the sense that it gets you, you can leverage your domain expertise. And if it's a very simple convex problem that's well understood, you might be able to kind of know ahead of time where the right solution is. What we find is this does not scale at all to larger, more complex systems, especially deep learning or more sophisticated machine learning pipelines. And at best, a human is able to find local optima in a very time-consuming and expensive way. At the end of the day, it's non-scalable, it's inconsistent, and doing it in your head is a very poor strategy when it comes to scaling. To fight this, a lot of open source tools have implemented things like grid search. This is the brute force approach to the problem. Just try everything and see what happens. It can work okay for very small dimensional problems. If you're just tuning a single dimension, you can just try a bunch of different things and see what happened. But as the dimensionality of the parameter space grows, this scales exponentially. And worse, as you start to have to space out the grid more and more, you're almost surely going to alias over the actual optima that you're trying to hit. So it's not scalable, often infeasible for more sophisticated problems, and can really limit the complexity that you allow yourself to search over. To combat this, and this has become popular in the academic literature, is random search or variants of random search like hyperband or early termination. These are great because they're a little bit more scalable than grid search, but they're largely extremely inefficient. More intelligent methods tend to get better results orders of magnitude faster. We've shown in several papers and blog posts with our partners like NVIDIA and Amazon that an intelligent Bayesian optimization search can get to better results 1 to 2 orders of magnitude, so 10 to 100 times faster than something like a randomized search. And if it matters how quickly you innovate and how quickly you iterate, I would highly recommend not just jumping out of an airplane and hoping you land at the peak, which is the equivalent of a randomized search. So there's a handful of ways that people have started to attack this in a more intelligent way, actually leveraging previous information in order to gain a slight edge when it comes to this black box optimization problem. Firms like Google have really popularized evolutionary algorithms. This can be effective for very specific spaces, like treed architecture searches, etc. They tend to be extremely resource intensive, though, because they require many, many different evaluations of the underlying population or model itself. And at the end of the day, tend to, again, be about an order of magnitude less efficient than methods like Bayesian optimization or sequential model-based optimization that really leverage the information that you get about the underlying system and then do a bunch of optimization on the models and the surrogate models that they're constructing about that system in order to drive you to better and better performance. The problem here, though, is while it can be extremely efficient and effective, it can be very difficult to administer, parallelize, and scale. And this was some of the pitfalls I saw in the open source before starting SigOpt, where it could be an extremely powerful method when applied correctly, but can be very difficult to apply correctly. And that's really where SigOpt comes in. Basically taking the cutting edge of all of these different techniques and more, combining them together, ensembling them in our patented and peer-reviewed way, and providing this clean interface so you can focus on your data, your model, and your backtest, the things that you can actually provide domain expertise to and create an edge, and then get this additive boost on top of that. Very efficiently getting new configurations, serially or in parallel, optimizing one or more metrics, doing so on very complex spaces with constraints, conditional parameters, potentially failed runs, and doing it with the full backing of our platform with enterprise insights, the actual enterprise scale, as well as that optimization ensemble. And it's worth repeating here that this is done at the black box layer, being IP and data safe from the very beginning. The actual model and training data and backtest stay within your environment and are never sent to or executed by SigOpt. What is sent to SigOpt is the configuration space of what you can tune. So the various tunable parameters of a system, maybe the learning rate or the number of hidden layers, the stochastic gradient descent method of a deep learning system. We report specific configurations to evaluate. Those are evaluated, and one or more objective metrics with or without noise are reported back. But only that configuration layer of information is sent to us, which allows firms like Two Sigma and the other asset managers that we serve to, with confidence, optimize their models, knowing no IP is ever sent over to us. Finally, I'll get to the fourth out of our fifth lesson here, maximizing resource utilization. This is extremely important when it comes to, again, iterating as quickly as possible. And you need to be able to say, what's worth investing in for my team versus what's worth investing in with a partner. And it largely comes down to, is there some advantage that I get by doing it myself? Do I have some domain expertise that I can kind of leverage and keep apart from my competitors? Is there something repeatable here that I can just set once and then not have to worry about again? Is there a large maintenance or reliability cost from using certain techniques? Often we say that the open source is free, which is great, but it's free like a pet is free. You can get it for free, but then the upkeep and the maintenance and the training and keeping it going is extremely time-consuming and expensive and can largely take on a life of its own. Optimization is a fun mathematical problem, but building a scalable resource that can service hundreds of quants across the world can sometimes be a very difficult and different problem. At the end of the day, you also need to trade off things like, are there more performant alternatives? Is the open source good enough, or can you get a much larger edge by bringing in a better, more sustainable solution? Is there a low maintenance burden? Is it something that can just completely bolt on? And at the end of the day, as I said before, it's about selecting the right tool for the job but not just the right tool for the job today, the right tool for the job in the future. So making sure that you have something that can scale and evolve with you. So an example of something that's well maintained and become an industry standard and really like continue to push the state of the art forward is something like Spark, where there's an active community, it's kind of constantly being pushed forward, and it's a culmination of many different technologies at this point. Many of the different open source, whether it be gPyOpt, which is what 2 Sigma explicitly compared us against in their use case, or Mo, which I wrote, or BaseOpt, or SMAC, which other SigOpt employees have written, are largely single approaches to the problem designed to solve a specific problem, publish papers, and push the academic field forward, which is incredible and why we continue to contribute back to the open source and is a great source of innovation. But at the end of the day, when it comes to scaling things, it's about being able to do so at that enterprise level, which is one of the main values that 2 Sigma emphasized in their blog with us. It's not just about having cool math, it's about being able to do that in a large enterprise environment, whether in this case meant being able to asynchronously schedule and parallelize various training jobs across hundreds of machines in their cluster to be able to take the training time of a specific model from 24 days down to 3 days, which meant not just getting the best model and putting it into production every month, but it meant better iterative performance, better ability to try different things, faster response to the changing markets, etc. And this is something that is largely lost upon kind of more traditional sequential model-based optimization. By being able to do this in parallel, by being able to do this behind a platform that can schedule and efficiently utilize large resources, it can take it from the academic world into the larger enterprise world. And we've shown this time and time again with our various partners, whether it's blog posts we've done with NVIDIA or AWS or others, where we've taken very difficult problems from the literature or from the open source community and showed by doing a little bit of tuning on top, you can get an edge. And I would encourage you to think about, for your specific problems that you're working on day to day, what could potentially be left on the table by not tuning or by using a suboptimal tuning method. And if it's as easy as bolting something on top with a few lines of Python, R, Java, MATLAB, or any of other client libraries, what that edge could mean to the business itself. And finally, the fifth lesson that we've learned from working with all of these firms is the ability to prioritize performance. And this goes down to, again, not just resource utilization on the machine side, but how do you do it on the personnel side as well? By being better, faster, and cheaper at this problem, you can iterate on more techniques, you can try more things, you can unlock self-constraints around what type of models you're tuning, how large the spaces you're tuning, etc., and be able to do so, again, with confidence, but also getting there in faster wall clock time, faster compute time, and faster expert time. And this is really what 2 Sigma found and the crux of why they chose us as a solution. They tried many different techniques, a lot of which I've spoken about in this talk so far. And at the end of the day, when they put us head to head against it, we were able to get better results faster and cheaper than any solution they had tried over the course of the history of the firm. More information on this is available on their website, where they talk about why they chose SigOpt as a solution. At the end of the day, one thing that's really important to us is our full-time research staff continuing to push the state of the art. If you go to sigopt.com/research, you can see a lot of our papers from NeurIPS, ICML, AI stats, some of the things that we've done with our collaborators at various universities or firms like Uber. This is very important for us to make sure that we stay at the cutting edge. And one of the things that has allowed us to do that is by having a very rigorous way to do internal testing. In one of our early ICML papers, we outlined this, a stratified analysis and evaluation system for comparing various black box optimizers. And this allows us to, with confidence, A/B test different methods and continually make sure as we pull in other techniques, as we pull in research from the literature, we're able to, with confidence, say, this is actually helping our real world problems. So we test against various pathological problems from the academic literature, but more and more, it's about testing against problems that look like our customers' problems. It's great if we can optimize some high dimensional pathological function, and that's wonderful for publishing a paper. But if we can see maybe some really difficult non-convex Pareto frontier that we had to optimize for a specific customer, we can start to build a bunch of problems that look similar to that and then rigorously test ourselves against it and be able to say, okay, how do we build the best optimizer, not just for academic problems, but for the many tens and hundreds of thousands of real world problems that we see at SigOpt, which has fundamentally shifted a lot of the techniques we use away from kind of classic problems to more real world problems. And this is something that's constantly evolving over time and getting better and better, but allows us to daily make sure that we're constantly pushing the state of the art. And what we've seen in this paper is that by, again, applying an ensemble of these different optimization techniques, it can vastly outperform other single approach problems, whether they be Gaussian process-based, tree Parson estimator-based, particle-based, evolutionarily based, brute force-based, etc. And a lot of this is from the paper from 2016, and it's only gotten dramatically better since then. A specific example that we talked about recently at NVIDIA's GTC conference was taking a classic problem in the computer vision space and showing what happens when you apply a good optimizer to it. So we took the Stanford CAR data set. This is an open data set that is an image classification problem. There's about 200 classes and about 16,000 images here. And what we showed was by taking a smaller, simpler network and doing fine-tuning with hyperparameter and architecture optimization, you can get significantly better results than taking a more complex network and just applying transfer learning and a little bit of tuning. So the takeaway here is instead of just assuming that problems are one size fits all, and in this case, you can take ResNet 50 pre-trained on ImageNet, and then just tune the fully connected layers at the end and say, okay, I'm just gonna apply a standard tools to this problem. By doing fine tuning, by doing hyperparameter optimization, by letting this system attack your specific problem, you can get significantly better results. So there's more detail in this on our YouTube page where I go into much more detail in our my GTC talk. But the main takeaway here is don't just use a one-size-fits-all solution. Make sure that you're getting the most out of these systems. Make sure that you're not leaving any opportunity on the table by not tuning or not fine-tuning, or again, just taking a one-size-fits-all approach. And this can have incredible implications when it comes to how much money it costs and how much time it takes to actually get to the best possible performance. Again, vastly overperforming even advanced sequential Bayesian optimization methods or more traditional randomized search, whether that be naive uniform sampling or something like hyperband / early termination with successive halving. And at the end of the day, it's about taking that performance and using it for these second order effects, trying more sophisticated models, trying to tune larger spaces, trying to tune entire pipelines simultaneously. So you learn a better feature representation to even be fed into a supervised learning algorithm, or being able to iterate on your metrics themselves by shining a light on something that you might not have been hitting because of your optimization engine before, but now can hit and say, now we need to adjust this to make sure it actually results in the best possible business outcomes. And we've invested a lot of time and energy in being able to do this well across real world enterprise problems, from being able to train over extremely lengthy training cycles, whether this is an extremely expensive backtest or a large deep learning system, from being able to look at competing metrics simultaneously, So being able to train against things like training size or time versus accuracy, or maybe a Sharpe ratio versus a book size, and really being able to give our experts that use our system the tools to be able to do not only optimization extremely well, but experimentation and iterative design of those experiments better and better. A lot of this is covered in the Two Sigma blog post that I've been referencing throughout this webinar. It's available on their website, and it goes into more detail in some of these specific pillars written by one of their managing directors, Matt Adareth. And with that, I will hand it back over to Nick, and he can answer some of the questions, or ask some of the questions that I will answer for you.
Thanks, Scott. Appreciate that, and we appreciate everyone who attended the webinar today. We'll run through at least a couple of the questions before we have to hop off today, and want to make sure that everyone knows, obviously through any of these links, you can actually get access to us. In the emails that have been sent out from my email address as well related to this webinar, just reply back if you have any specific questions, and I'll make sure that we triage internally and get the right answer to you as well. So even if you have questions that extend beyond the constraints of this particular webinar, we'll make sure that we get you an answer as quickly as possible. So Scott, first question that we had here was related to the Two Sigma interaction that you've had more specifically, and this question is just basically around the scope of your engagement with them, whatever details you're willing to share. There's not that much context provided up front on that particular relationship, so just a little bit more detail on how we actually work with them today.
Great question. So Two Sigma has been a customer of SigOps for a while now. We recently kind of upgraded our relationship into a strategic partnership, which includes a minority investment in SigOps because they found it so strategically useful for the firm. So Two Sigma Investments directly invested in SigOps. It's worth noting, though, that we take our privacy and security extremely importantly, and we think it's extremely sensitive. So even with this investment, they have no extra knowledge about any of our other customers. They're not even aware of who our other customers in the space are. They don't get proprietary access to any technology that isn't also available to other customers. And there's no information exchange about customers or techniques or anything that we learned from the field. So again, they found it extremely strategically important for their firm, and they very rarely make direct investments directly from Two Sigma Investments as opposed to their venture arm. But they did so in our case. But again, it's much more to maintain access and to show the strategic alignment, and does not give them any special access over any of our other customers.
And to put a finer point on that, in terms of the actual product relationship, can you shed any detail on how they've integrated SigOpt in their stack?
Yeah, so they've definitely kind of, as Matt Greenwood said in a recent talk I gave with him at O'Reilly AI, he's their chief innovation officer, they've put it everywhere. So they obviously do a lot of machine learning. They do a lot of deep learning with hiring of Mike Schuster from Google, who was on the original TensorFlow paper. But they also use us to tune trading strategies, their actual infrastructure environments. Matt Greenwood even said they've used us to tune the JVM itself. Really anything with tunable parameters where you have some measure of success, you can bolt us on top and continue to push that edge forward. So it's incredibly pervasive across their researchers, their platforms, but also their hardware and infrastructure.
Awesome. Another question came up around comparisons between SigOpt and other industry-specific optimization solutions. I think in particular, they're asking about some portfolio optimizers and other types of systems that seem like they're pretty standard in finance, but maybe a little bit different from what we do. So shedding light on that would be helpful too.
Great question. So inherently, SigOpt differs from something like a portfolio optimizer, like something that Axioma or something could provide, because we're solving a black box optimization problem as opposed to a portfolio optimization problem. The difference there is we want to be able to take a system that you have maybe no strong assumptions about how it behaves, like a deep learning system, a trading strategy, etc., and be able to, in a very black box way, get you to the most performant results as quickly as possible. Versus a portfolio optimization strategy, which can make extremely strong assumptions about maybe the convexity of the space, be able to apply kind of more traditional optimization approaches to it, like interior point methods, etc., to be able to solve a very specific problem very narrowly. We want to solve a very broad problem very efficiently. So we can work hand in hand with a tool like that. Often portfolio optimization problems have their own tunable parameters associated with them, but you can think of us as, instead of optimizing a portfolio, we're going to optimize the models, the strategies, the infrastructure, and everything that goes into that portfolio.
Yeah, and the way I think about this from a less sophisticated perspective is that we're highly complementary to those types of approaches. We often, almost every company that we work with obviously uses some version of that optimizer in conjunction with our product as well, largely because we're solving different problems. So we've actually, in fact, even explored, at least in early days, some partnerships that could end up going, helps cementing that more formally over time as well. Next question is around the affordability of our product for startups. So without getting into details, I guess commenting on the way that we typically structure our relationships could be helpful here.
Yeah, so our pricing model is based off of usage. So the number of experiments or models that you tune on a given month. We sell annual contracts associated with specific tiers of experimentation. And that can vary from hundreds of experiments a month for smaller firms up to many thousands of experiments for some of the larger firms that use us. So we have a couple of special plans that can help people just getting started. One thing is our academic program. So anyone doing public peer-reviewed research as part of a university or national lab can use our service completely for free. They go to sigopt.com/edu. We have hundreds of universities around the world publishing papers using a lot of our techniques. Depending on the size of a startup as well, we'd be happy to try to talk about ways that we can help grow with you. So I'd recommend reaching out to contact@sigopt.com, and we can provide more granular detail. But for our large enterprise customers and asset management firms that we support, it's largely the subscription-based service based off of usage, which we think is strongly correlated with the value we provide.
Mm-hmm. Yeah, and I'll comment just that, especially startups who are AI or ML first, they do typically find that both our price is affordable for them, but also ends up providing kind of 10 times the value that any cost that we incur for them, largely because models are core to what they do. Great, and that's actually all we have time for in terms of questions today. So I appreciate everyone who's attended and stuck through to the end with us here. If you have any additional questions, I think most people know where to find me in particular, but if not, Scott also mentioned you can either email contact@sigopt.com or you can navigate to a couple different ways to try our product by just visiting sigopt.com/try-it and get a better sense of how our product could potentially fit for you. So we appreciate your time today, your attention, and I hope for those of you in the Bay Area, you're getting outside to enjoy this 70-degree and sunny weather. Thank you.
Bye, everyone.